Hi, I'm Dave Mueller, retired hydrologist from the U.S. Geological Survey and founder of Genesis Hydrotech. In this session, I'm going to discuss using GPS with ADCPs. GPS provides an alternative navigation reference to bottom track, and because of this, it is the preferred reference for ADCP measurements when the bottom track data are biased by a moving bed condition. GPS can also be used if the ADCP is unable to bottom track reliably or to quality assure bottom track data even if no moving bed condition exists. There are some things to be aware of when using GPS, however. First, directional bias is possible when using GPS. This directional bias may be caused by compass errors and errors in the magnetic variation used, two issues we'll discuss later. But for now, remember an accurate heading is very important when using GPS. Collecting transects in reciprocal pairs helps to average out these directional biases. GPS tends to have a higher standard deviation in the measured discharge compared to the bottom track, as the data typically has more noise. There can be issues with invalid or questionable data near the banks due to something called multipath errors, another topic we'll cover in this lesson. These data quality concerns make monitoring of collected data an important part of using GPS. Now let's talk about some of the recommendations for GPS receivers that will be used with ADCPs. First, the receiver must be capable of receiving differential corrections. Differential corrections can be obtained through services with a fee like Atlas, or services that are free and readily available here in the United States like WAS. These differential correction services enhance the quality of the location data by applying real-time corrections for things such as atmospheric interference. The GPS receivers must also have an NMEA 0183 output that includes both GGA and VTG strings. The NEMA 0183 is a standardized format for data communication between marine electronics and is recognized by ADCP manufacturer software. The GGA string must have at least 5 decimal minute precision, and the VTG string should have at least 2 decimal precision for speed. Less precision could introduce errors in the computed boat speed when using GPS as the reference. The receivers must be capable of outputting both VTG and GGA data at a minimum of 2 Hz, twice a second, and have minimal positional filters. Typically, handheld GPS receivers do not meet the above requirements. The GPS reference provides position data, but no velocity. Velocity is computed from 2 consecutive GGA sentences by computing the distance traveled and dividing by the time between them. GGA data should be differentially. The errors in GGA data tend to be easily identified. Perhaps the largest source of error in GGA data is multipath. The GGA sentence includes an identifier, a timestamp, the latitude and longitude, a quality indicator indicating if differential correction was applied, the number of satellites, and a measure of HDOP and altitude, both of which are used to evaluate the quality of the GGA data. Multipaths are caused by a reflected signal in lieu of a direct signal. Trees, bridges, steep banks, buildings, water, and other obstructions can cause the GPS signal to reflect, resulting in significant position errors. These two sites have a high potential for multipath errors. The one on the left due to the bridge, and the one on the right due to the trees. The VTG sentence provides velocity only. The velocity is computed based on the Doppler shift from the satellite signals to the receiver. VTG data are not affected by multipath errors, and they do not require differential correction. VTG can be a valid alternative to GGA, especially when differential corrections cannot be obtained. However, the errors in VTG data are more difficult to detect and seem to be more common when boat speeds are less than about 25 centimeters per second. The VTG sentence contains an identifier, the course reference to true north, and the speed in both knots and kilometers per hour. When setting up a GPS receiver, there are several things you need to be aware of. First, be careful of built-in features. Some can cause a lag in the data. The update rate is also important. It is preferred that at least one GPS position and/or velocity be obtained for each ensemble. This translates to an update rate of at least 2 Hz, with a preferred update rate of 5 Hz or higher. Rates of 10 Hz and higher may cause problems with some computers and software. Also be aware of the baud rate. The baud rate must be sufficient to handle the data throughput. This table provides some reasonable estimates. If the update rate is too high for the baud rate, the GPS may buffer data, resulting in GPS data lagging behind the ADCP data. Your serial port is important. Old computers had a hardware-based serial port using a UART 16550 chip. New laptops, if they have serial ports, are typically an internal USB-based serial port. Many USB-based serial ports are problematic. USB serial ports based on the FTDI chip and firmware seem to work the best. However, it is important to test your ports with the ADCP and GPS before going to the field. This time series plot shows an example of GPS lagging bottom track. The ensembles are increasing from left to right, and we can clearly see that the red line representing bottom track reacts to changes faster than the green or blue lines representing VTG and GGA. You can also see a lag in GPS when making quick turns with the ADCP. In this ship track plot, you can see that the bottom track, red line, turn and begin to return back to the starting point, while the green and blue lines representing VTG and GGA continue along in the original direction. The position of your GPS antenna is also important. It is recommended that it be placed directly over the ADCP and higher than any of the rest of the deployment. Placing it higher than any of the deployment will help reduce the potential multipath errors. Also, by placing the GPS over the ADCP, you will avoid potential problems when turning the boat. In the diagram at the far right, you can see that the ADCP is located near the rear of the boat, but the GPS is near the front of the boat. When the boat turns, in this case, turns to the left, the GPS antenna moves to the left. However, because of the center of rotation of the boat, the ADCP moves to the right. Thus, the GPS velocity would not be consistent with the velocity of the ADCP. For TRDI ADCPs, there are a couple of options for integrating the GPS. For any of the instruments, the GPS can be transmitted directly to the laptop, but this requires a second serial port on the laptop. When configuring TRDI ADCPs in this manner, the external GPS should be checked in the configuration wizard. However, the RiverRay, RiverPro, and RioPro have the option to integrate the GPS signal directly into the ADCP. In this situation, the internal GPS and the appropriate baud rate should be configured in the configuration wizard. This baud rate is the baud rate of the GPS. The potential issue with the RiverPro, RioPro, and RiverRay when routing the GPS through the ADCP is when the processor is processing the bottom track or water track data, it cannot service the GPS port. This could result in some GPS data not being received. To minimize this problem, it is suggested to use a higher baud rate and update rate to help ensure data are available at the port when the processor is ready to receive it. For most SonTek ADCPs, GPS is purchased with the ADCP and is integrated into the system communications. However, it is possible to use an external GPS with River Surveyor Live. To do so requires the communications protocol be set to 38,400 baud, no parity, 8 data bits, and 1 stop bit. The data update rate must be 10 Hz. Only the GGA and VTG strings should be transmitted. To avoid possible communications issues, it is always recommended to turn off or disable any additional GPS strings being output by the external GPS receiver. An external GPS receiver can also be used with RSQ. The communications protocols are the same, but the update rate and strings utilized are different. The table at the bottom right shows the update rates and data strings used by RSQ. So why is the GPS so important when using GPS? If we look at the figure on the left, representing bottom track, we can see that the boat vector for bottom track is referenced to the orientation of the instrument. Likewise, the water vector is referenced to the orientation of the instrument. When we look at the equation for discharge, we see all that is needed is the magnitude of the water vector, the magnitude of the boat vector, and theta, the angle between the water and boat vector. Because both the boat vector and water vector are referenced to the orientation of our instrument, the orientation of our instrument is really unimportant. This is why the Stream Pro can measure discharge with no compass. However, when we look at the figure on the right representing use of GPS, we see that the water track is still referenced to the orientation of the instrument. But now the boat vector using GPS is referenced to true north. Therefore, to get both the water vector and the boat vector referenced to the same reference plane, we need to know the magnetic declination, or variation, and the heading of the instrument from the compass. Where do you get magnetic variation or declination? There are many options. You can Google it. Or use one of the many available phone apps. I use an app from NOAA called CrowdMag. Directional bias occurs when there is a constant error in heading, such as when the magnetic variation is incorrect. Fortunately, the mean of the reciprocal transects results in a value very close to the true mean. Making small adjustments to the magnetic variation will improve the random error computed in uncertainty models, but will have little effect on the final discharge. Using some equations that I published in a paper on the effect of compass errors on ADCP measurements, we can estimate the error in the final discharge from the average reciprocal transects. If we assume the water velocity is perpendicular to the boat velocity, the published equations reduce to the first two equations shown here. The first being the discharge error for the left to right transects, and the second, the error in discharge for right to left transects. To compute the error of the average of the reciprocal transects, we add these two equations and divide by 2. When we add these two equations together, we see that the term with the sign has opposite signs, and they cancel. We're left with just the cosine of the error minus 1, which reduces to about 0.06% for an error of 2 degrees. Thus, the error that occurs in the final discharge when averaging reciprocal transects can be approximated as a cosine error. Heading errors are not consistent. The diagram shows the distribution of heading errors that remained after a river ray compass has been calibrated. So when the orientation of the ADCP is changed, the heading error is not constant. Thus, this error does not cancel when averaging reciprocal transects, but results in a bias. Applying this unequal error and averaging does not result in the cancellation of the sign term. We do not know the heading error. If we did, we would correct it. ADCP compasses typically have a specification of plus or minus 1 to 2 degrees. We can simplify the previous equation with little error. The important term in this equation is the multiplier on the sign term. It is the ratio of the magnitude of the boat speed to water speed. Given some heading error, the bias in our discharge increases with increasing boat speed compared to the water speed. When using GPS, going slow will minimize error in the discharge due to unaccounted for heading errors. Graphing this equation for different heading errors and different boat speeds, we can see that a heading error of 2 degrees with a boat speed twice the water speed will result in a 3.4% bias in our final discharge. In summary, use of GPS is preferred over bottom track in moving bed conditions, but this requires a clear line of sight to the satellites, accurate compass headings, and a magnetic variation entered into the ADCP software. With all ADCP data, including GPS, it is important to monitor your data during collection to catch errors. It is also recommended that you operate the boat to go smooth, steady, and as slow as practical while maintaining control. Once you've selected the highest quality reference, whether it is GGA or VTG, use this same reference for all of the transects making up your measurement, unless there are obvious reasons to change.